Okay. I want to talk a little bit more about this idea that the work done by a gas on its environment is the integral of pressure over volume, pressure dV, as the volume changes. And keeping in mind also that we're thinking about it in terms of this equation, the first law of thermodynamics. It says that if you want to change the internal energy in your material, you have to either add heat or you have to have something do work to your thing where work would end up being negative. Or in this case, you want your work to be negative here in order to add it. Or you could, if you have your gas and it does work on something outside of itself, that means it's losing energy. It means its total internal energy will change. And we also should remember that the change in the internal energy is going to be F over 2 little n times r, the change in temperature, or we can write this in terms of capital N and K, change in temperature. And these are from earlier videos. So a bunch of different situations can occur. So if your volume stayed constant, so your gas doesn't expand or contract, well, if there's no change in volume, then there's no work. Right? If you look at this equation, if there's no change in volume, there's no work. And we even saw that over here with step B to C. There's no change in volume, there's no work. And that means that the total change in internal energy is just coming from heat. Well, the total change in energy is this thing. But heat, if you remember, if we're changing temperature, right, way back in the first chapter, I had that if you wanted to change the temperature of something, you'd say the mass time of the total part of object you've got, this is your whole sample, times the specific heat of the sample is times the change in temperature. So, if you want to change the temperature, there's some dependence there. Another way of writing it, instead of doing mass, is you could say the number of moles times the specific heat per mole, or the heat capacity at constant volume per mole. So the heat capacity at constant volume is similar. So here, the mass of our sample times little c would be the same as n times z, as long as we're talking about the volume staying constant, which is most of the time true, especially for a liquid. Not all things stay constant, but some things do. A gas would change volume probably. And so we can have this as our equation, and this is sort of a little shortcut. And then the heat capacity at constant volume is, by the way, F over 2. Oh, goodness. It's F over 2 times R. So all that matters here is really, this is for gases, which is very convenient. Now, if instead of the volume staying constant, which is a little hard to do, especially for a gas, but if instead your pressure stays constant, now this is very typical. It is very typical for things to have constant pressure at the Earth's surface, because the atmosphere of the Earth really helps regulate the pressure of anything that occurs in the regular atmosphere of the Earth. Now, if you're doing it inside some sort of, closed vessel, your pressure can change. But if you're doing a reaction or something like that, if you're a chemist and you're doing a reaction and it's open to the Earth's atmosphere, the atmospheric pressure is going to stay the pressure of your reaction, and so your pressure will stay constant. If pressure is constant, then this integral, right, if pressure becomes a constant, then you can bring the pressure outside the integral, and so you're really only left with the work is equal to the pressure times the change in volume. And so your change in internal energy is the Q times, or subtract the work. So bringing that all down here, and so this is essentially the change in the internal energy is 1/2 F NK, and I'm sorry, sometimes I write that as Boltzmann's constant as a K with a little b. We'll just write it as a K. So this side we have the change in internal energy. Here we have the amount of energy I have to put in to change the temperature when the pressure is constant. So this capital CP is the heat capacity at constant pressure per mole. So how much energy do I have to put in to change the temperature if I keep constant pressure, not constant volume? And then I'm going to subtract off of that P delta V. Well, P delta V, right, if we have the change in pressure, if this is an ideal gas, this is a gas, this is NKT. So if I have some change in volume, that's being caused by some change in temperature. And so I can write, again, let me get rid of that little K sub B. So I have N, K, delta T. So I have a delta T on both sides here, and I can get that the CP, the heat capacity at constant pressure per mole, is F over 2 plus 1 times R. Well, this is just CV. So if you want to change the temperature of your gas at constant volume, it doesn't take as much energy, as much heat as it's going to take if you want to change the temperature at constant pressure. At constant pressure, you're going to allow the thing to expand in space, and so you have to add more energy in to make that happen. And so if you go and look at tables of CV and CP values, they're very, very constant, and CP is pretty much always just an R 8.31 larger because of this very rule. You can also have temperature stay constant. This would be isothermal. If the temperature is constant, then F over 2 NK delta T is 0. And so you have no change in internal energy. If that also means that if temperature is staying constant, then you can put in, for an ideal gas, you can put in that the pressure is NKT over V, and T is a constant. And so you can bring out that NKT. So in my integral here, I'd have NKT over V delta dV, and so I can bring my NKT out, and I end up with dV over V, which that's the natural log. And so I end up with that the work is equal to NKT, the natural log of the final volume over the initial volume. Since I have that the internal energy change is 0, that means that Q is just equal to negative that work, or negative K. I just have KB written down everywhere here. Negative KT, natural log of BF over B naught. We're going to use that in just a minute. You could have situations where something is adiabatic. So adiabatic means that Q is equal to 0. No heat flows in and out. Generally, these are very fast processes because you got to be really fast in order for Q not to flow in and out of something. But if Q is equal to 0, then the change in internal energy is just negative work, or is negative P delta V, or the derivative integral of P delta V. I'm not going to do this proof, but in adiabatic processes, this strange product of pressure times volume to an exponent, where the exponent is this ratio of Cp over Cv called gamma, is constant amongst between these changes in pressure and volume. And so you can use that relationship to find new pressures and new volumes, or old pressures and old volumes. And then there is, if you expand into a vacuum, then actually everything is zero. If you have a gas and somehow there's a vacuum, the gas can expand with, the temperature won't drop. You'll have zero change in temperature because all their energy is still in there. They don't lose any energy. They just spread out, but they don't have to give up anything. They don't have to gain any Q. They don't lose any work. They don't change their internal energy in free expansion into a vacuum. Let me do, this is entirely different, but let me talk about this briefly. This is real thermodynamics kind of stuff. And thermodynamics is actually much easier than thermal statistics. Thermodynamics is looking at things from sort of a big process kind of way of looking at things, like engines and refrigerators and heat pumps. These all use cyclical processes. So an engine has to cycle through, right? It goes over and does the same cycle over and over and over and over and over again, and your car just drives forward. Or a refrigerator does the same thing. A heat pump, anything like this, it goes through what we call a cyclical process. This is a cycle of pressure and volumes and temperatures that it repeats over and over again. It typically, as it goes through this process, it will gain and lose heat to a hot reservoir, which we call Q sub H. Q lost to a heat. Sometimes it's gained to a heat reservoir. Sometimes it's lost to the hot reservoir. It will gain or lose heat to a cold reservoir. And then typically it will either use or produce work, depending upon what your thing's trying to do. So, and usually we draw this weird cartoon for these things. I think they even have some in here for this. Like there's this weird little cartoon. So say just an engine. You draw like a kind of an area up here, and I say, well, this is where my hot reservoir is, and you say, well, the temperature of my hot reservoir is TH, and I have a hot reservoir. So the hot reservoir, this is going to be the location where you're burning something. So the pistons where you're burning the energy, you burn it. And so you're going to get, in the case of an engine, we burn something, and that heat, Q sub H, goes into our engine. The whole point of an engine is to get work out of it. And so we're going to get work out of our engine over here to this over here. So getting work out. And then after, the engine actually expels heat to the outside of my car, right? The heat gets dropped out, goes out the tailpipe where it actually produces all heat all over the place, but it produces heat and it dumps it outside to the cold reservoir, which in the case of a car is just the outside. So looking at this, what we always do is we write an equation here, which is the conservation of energy equation, where we say the energy that comes in to this engine area has to equal the energy that goes out, because the total change in internal energy has to be zero. So the energies that's coming in here is just QH. The energy that's going out is the work and QC. And so there's my relationship between work and the heats that are involved. All energies have, all cycles, all cyclical processes, things like this, have either an efficiency, or sometimes they have, sometimes I don't want to call them that, like with heat pumps and refrigerators, they don't want to call it an efficiency, they want to call it a coefficient of performance. But it's always going to be the benefit of the cycle, the reason you're doing the cycle, over the cost. What do you have to put in to make the cycle happen? So in the case of my engine, the benefit is the work, right? but the cost is the Q sub H. I have to produce the heat by burning something. So that's my cost. The thing I'm trying to get out of my engine is the work. So I can, oftentimes you can do a little bit of math here, right? So work is equal to Q sub H minus Q sub C. And so you can write that in here. And you can essentially sort of combine your situations. Here on the diagram in the book, they actually have a refrigerator, which is sort of the opposite in many ways of an engine. Here you actually have a cold reservoir, and the point of a cold reservoir is to take heat from the inside, right, of a refrigerator is to decrease the temperature in the cold reservoir. And so you actually remove heat from the cold reservoir. You have to get electrical energy to make this happen, and so work comes in, and then you dump heat to your hot reservoir, which is the outside, which is your kitchen. And so in the case of a refrigerator, your energy in is QC and W, and your energy out is QH. With a refrigerator, so I'll write this off to the side. With a refrigerator, here we do have a coefficient of performance where, again, we want to put our benefit. Well, why do you have a refrigerator? You're trying to remove QC, right? That's our benefit. And then the cost is the work. We have to pay for electrical energy to make this happen. Since our relationship of energy was that QC plus work equals QH, I can rewrite QC. I may write it the other way around. I can rewrite work as being, again, QH minus QC, and so I can end up with QC is equal to QH minus QC. And again, you end up with this sort of very specific relationship here. And you can play these things all over the place. So I think their writing is capital K for their coefficient of performance, but I think we have enough K's, don't you think so? I do. I'm going to do this last one in these last things in the last video. Okay.